So now that we have discussed schedulability, it is important to look at what happens in the case of locking and acquiring resources. So assume that we have a low priority task T low that acquires a resource. And let's say its priority is 5. And then there is a higher priority task T high that comes. And let's say its priority is 20. It will not, well, it will preempt T low, it will run until it stops at the point of acquiring the resource R. Because R has already been acquired by T low, so T high would kind of stop over there. T high would stop over there, and even though its priority is high, it doesn't have a choice. It will have to let T low to execute, right? So T high will go till this point, but then T low will run, and T low has a priority of 5. So this sounds unfair because a high priority task is not able to run because a low priority task is holding on to a lock. But still, nothing can be done because we can't take a lock away. So it has to wait. But things can get even more unfair if it is preempted by a medium priority task whose priority is, let's say, 10. In this case, what will happen is that T high, which is waiting on T low, that is fine. The first part is fine because it was trying to acquire a resource which was previously acquired. But now the point is that another task T medium with priority 10 has preempted T low. It is running. That can get preempted by another task T medium prime with, let's say, priority 12. That will keep on running. So T high will get preempted by a large number of tasks which have actually not acquired a resource, but their priority is intermediate between 5 and 20. So this is a case of priority inversion, and it is sadly a case of unbounded priority inversion because you don't know for how long this is going to continue, right? So T dash medium may be done, but then another intermediate priority task will come. This can actually continue for a very, very long time. There is no bound. So a solution is that we temporarily, so let's say T high, and I'll discuss the solution in a second. Its priority is 20. It keeps running until it tries to acquire resource R, and that's where it gets stuck. Then we have T low that is running, and T low has a priority of 5. So one solution is to temporarily boost the priority of T low to 20 such that it starts running with priority 20, but this is a temporary priority. Then what happens is it releases resource R, and then T high starts running with priority 20, and the priority of T low becomes the priority that it had prior to acquiring the resource, which is 5. So the priority inheritance protocol, what it does is the moment T high starts waiting on T low, it raises the priority of T low to that of T high, which is 20. So basically 5 becomes 20. Sorry, 5 becomes 20 the moment T low, 1 second, the moment it should be T high actually. So let's see. So T low's priority from 5 it becomes 20 the moment T high waits on T low. So this is known as priority inheritance because the priority of T low is temporarily increasing from 5 to 20, something like this. 5, this is where the wait event happens. So it becomes 20. This is where the release event happens. So it becomes 5. So an advantage of this is that all those intermediate priority tasks that were actually blocking T low and in effect blocking T high, right? Because if you think about a task whose priority is 12, it should ideally not run because T high should run, but because its priority is higher than 5, it was blocking T low and T low was blocking T high. So T high was getting blocked because of a large number of tasks. That will not happen if T low temporarily inherits the priority of T high. So we have already seen unbounded priority inversion, which can happen if there is no priority inheritance, but priority inheritance stops unbounded priority inversion. But there are many more things that can happen. What can happen is that we can have chain blocking where T1 waits on a resource that T2 needs, T2 waits on a resource that T3 needs, so on and so forth. Chain blocking is possible. If chain blocking is possible, well, you can easily see that they can deadlock also. That also is possible. Then there is something called second blocking, which is a term that is actually introduced in our book. It's not a standard term, but it is very useful. And this will be used to prove a lot of lemmas and theorems. It says that if task T acquires a resource R, so assume task T acquires a resource R. Subsequently, perhaps after acquiring or releasing or whatever, it gets subsequently blocked when it tries to acquire another resource, right? So this is known as second blocking, right? That after acquiring the first resource, it actually gets blocked while acquiring the second resource. This is second blocking. This can happen in the PIP protocol in the sense, why not? That once something is acquired, then it tries to acquire something else, but that has been acquired by another task. So second blocking is this. So it's not chain blocking. Chain blocking is different. In chain blocking, you have a chain. Second blocking is from the point of view of a task that if it has already acquired one resource, if it is getting blocked while acquiring any subsequent resource while holding the first one, like a nested acquire, then this situation is known as second blocking. So there are some simple relationships. If we can prove that in a protocol there is no second blocking, you can easily prove that there is no chain blocking. So consider chain blocking. So the contrapositive of this would imply that chain blocking implies second blocking. All right. So basically, no second blocking would imply no chain blocking. So consider a case of chain blocking T1, T2, T3. So any such pattern, if you look at T2, what has happened? T2 has acquired a resource which T1 is later trying to acquire, so T1 is getting blocked. And T2, after acquiring one resource, is actually executing for some time and then blocking on T3 because it is not able to acquire some resource that T3 has. This is a classic case of second blocking. So this basically means that if chain blocking is there, you will have second blocking for this task T2, which after acquiring the first is getting blocked while trying to acquire the second. So since chain blocking implies second blocking, no second blocking would imply no chain blocking. Similarly, no chain blocking would imply no deadlock. So consider the contrapositive. So let's say that there is a deadlock. That would imply that there is some degree of, some instance of chain blocking. That is indeed the case. In fact, the circular wait condition or in the hold and wait condition also, both of them are this that consider. So this pattern is needed for a deadlock. T3 could be same as T1. And here clearly this is deadlock would imply that such a pattern exists, which is a chain blocking pattern. And clearly if I am not having patterns of this type, which means there is no chain blocking, clearly there will be no deadlocks. So what is important here? It's important to understand that if I'm able to prevent second blocking, And preventing second blocking means what? It means that after a resource has been acquired, pretty much the task has an absolute right to acquire any other resource that it wants. That will, without blocking, right? So if that can somehow be ensured that there is no second blocking, then you can ensure that there is no chain blocking, which will further ensure that there are no deadlocks. So this becomes a very important property for us. So let's look at the first such example, which is the highest locker protocol, which is a smarter protocol. So here we'll have to make an assumption which most students find hard to digest, which is that consider a resource R. Let us assume that somehow we know all the tasks that are ever going to ask for resource R. How we know is not important. We somehow know the set of all the tasks that are ever going to try to acquire R. Right now or in the future, doesn't matter. At some point of time, they may ask, it's not that they will ask, but they may ask for resource R. If this set is S, it clearly means that in, let's say, the complement of S, no task can ever ask for a copy of, for resource R. So if this is known, we can take the priorities, original priorities, not the boosted priorities because of inheritance, the original priorities and find their maximum. So which would be the maximum priority of any task, let's say P element of S, right? It's maximum of the priority of that task, right? So it should be, maybe I can write it better. I can make it T element of S. So let me just quickly. So I consider the set S, which is the set of all the tasks that may ever ask for resource R. I consider a T, and I take the maximum priority, right, of all such tasks. That is the ceiling of the resource, right? That's a very important thing. A ceiling is a hypothetical thing that it's the largest priority of any task, largest original priority of any task that may ever ask for resource R. So this is a simple algorithm. Once a task acquires a resource, we simply raise its priority to ceiling of resource plus 1 if this is lower than its current priority, else nothing is done. So what are we doing? What we are doing is consider a resource R, let's say. Let us assume that three different tasks may ever try to acquire it, right? T1 with a priority of 5, T2 with a priority of 10, and T3 with a priority of 20. Let us assume T1 is executing. It tries to acquire resource R. Its current priority is 5. After acquiring resource R, T1's priority will become ceiling of the resource, which is ceiling of the resource is in this case 20. So it will become 21. So then T1's priority will become ultra high. It will become ceiling of the resource plus 1 if its current priority is less than it. Otherwise, its current priority will continue. That is exactly what it is going to become. Ceiling of the resource plus 1. Of course, there are, it is possible to prove that the current priority will always be less than this, but that is slightly complicated. Hence, I'm not going there. The fact is that the priority, if I set it in this manner, where every time a resource is acquired, it is going to be ceiling of resource plus 1. If that is how I increase my priority, then what can happen is theoretically there could be a task T4 which is interested, whose priority is 100. So the moment T1 acquires, instead of 21, its priority will become 101. Then it will pretty much be able to block every single process. Well, not block it, but preempt it, not allow it to run. And a large number of tasks will not be able to run precisely because T1's priority has become ultra high. So this is also known as inheritance blocking because in a certain sense T1 acquired a resource, it kind of became a superman, and it effectively what is called inheritance blocked everybody else. It's quite unfair if you think about it. So the terminology that we shall use in the subsequent part of the proof is that let T1 be a task, let its current priority, which can be affected by priority inheritance or by its priority being raised because it acquired a resource in the highest locker protocol, let that be priority C, priority current. And let priority O, meaning original, be the original priority of T1, right? What it started with. So let us actually prove that a lot of good properties are ensured by the HLP protocol. So if you would just go back to the previous slide once, we will just to remind we have these two priorities and the fact that the current priority can actually be quite high. This is something that we shall use to prove that there is no resource related blocking in the HLP protocol, which means that it will never be the case that a given task is trying to acquire a resource and is getting blocked. Instead, it will not run in the first place. See, a task gets blocked while acquiring a resource if it is running. So it runs, it tries to acquire, it gets blocked. But if it is not running in the first place, it can never get blocked. We will use this logic to say that there is no resource blocking. No blocking means resource blocking in the HLP protocol, right? Inheritance blocking is there, but we are interested in resource related blocking. So let us look at a situation where task T2 acquired resource R at time T0 and T1 while trying to acquire resource R, while trying to access and acquire it, uh, it gets blocked at time T block. Let this be the first such instance of a resource blocking that has been recorded in the system. That's very important, which means that prior to T block, there was no instance recorded where a task actually got blocked while trying to access a resource. This is the first such instance. So the question is that at T0, what was task T1 doing? The first is it had not started. So if it had not started, then the following relationship holds that the original priority of T1 has to be less than equal to the ceiling of resource R. This is by definition, right? This is follows from the definition of a ceiling because T1 is interested in the ceiling. If you are not able to understand this, go back, figure out the definition of a ceiling, and come back to this point. Now, clearly, the ceiling of R is less than the current priority of T2 because at this point of time, T2's priority is at least ceiling of R plus 1. So, this has to be the case. And given the fact that T2 is not going to block while acquiring a resource, it can get preempted, but then whoever is going to preempt it is going to have a much higher priority. The question is that T1 will not get a chance to run. The reason it will not get a chance to run is because T1 has not acquired any resource, so it is simply running. And basically T1 has not started. When T1 starts, it is starting fresh with its original priority. At that point of time, T2 has a higher priority. Either T2 is running or some other task that has a much higher priority than T2 is running. That will clearly not allow T1 to start. And because those tasks with a higher priority will not get blocked before T block, T1 is not even going to get a chance to run. If it does not get a chance to run, how is it the case that T1 ran and was trying to acquire R and at that very point it got blocked? That is not possible. So if that is not possible, we need to consider the other case where T1 had already begun at some point prior to T0, right? Which means T1 had started, and at T0, the reason that T2 was running is because T2's current priority was higher than T1. So what we know is that T2 started running, it acquired the resource, so it could not have been blocked before T block. Correct? So before T block, there was no way it could have been blocked. That is our assumption, that before T block, no task gets blocked, right? Resource block. So this will, so what can happen? So what can happen is that some high priority task can preempt T2. So if some high priority task is preempting T2, fair enough. Let that task be TH, right? And its priority is very high. Now the question is that if you assume priority inheritance, it is possible that it blocked on some resource that T1 had acquired and transferred its priority to T1 such that T1's current priority actually became higher than T2's current priority, and T1 started running. And then, as you can see, T1 ran, and then T1 tried to acquire a resource R and got blocked. But hold on, this is not possible. The reason this is not possible is because no task which includes TH, hypothetical TH, can actually block before T block and transfer any priority to anybody. So nothing of this nature is going to happen, which basically means that, let's say at T0, if T2 had a higher priority and T2 is not going to get blocked before T block, it is going to continue to run. Either T2 will run or some other high priority task TH which will preempt T2 and that will run. But none of these tasks are going to get resource blocked. They can only be preempted by higher priority task, which means that T1 is never going to get a chance to run again before T block. Hence, the probability that T1 will actually run and then get blocked, that is zero. That's not going to happen. The reason it will not happen is because T2 will not allow it to run. So we clearly have a much stronger result on our hands that in HLP there is no resource blocking. If you want me to be more precise, there is no resource blocking. Inheritance blocking there is plenty, but there is no resource blocking. If there is no resource blocking, by definition there is no second blocking, which by definition there is no chain blocking. By definition there are no deadlocks. So this kind of solves a plethora of issues just by raising the priority of a task. That solves a lot of problems for us. But it introduces a new problem, which is inheritance blocking, which means that a task's priority actually becomes very high, right? And because it becomes this, it becomes tough, right? So it becomes very, very high. And that is an issue. So I would like to slightly correct myself. I had said something that now I realize is incorrect. That ceiling of R plus 1 will always be greater than the current priority. That's actually not correct. So I would like to correct myself. And that is because you assume a resource where only one task is interested, and that has, let us say, priority 5. Then the ceiling R plus 1 is going to be 6. But it's possible that prior to that, the task has acquired some resource whose ceiling is 100. Then its current priority will be 101. So that is why what I said there is not correct. So I would like to correct myself. But broadly speaking, this is the HLP protocol where we proceed in this fashion. So let us look at the priority ceiling protocol that tries to solve some of the issues of the HLP protocol, especially inheritance blocking. So the main idea here is that we are slightly intelligent. Many times, even if a resource is free, we do not allocate it. And this is what gives us some amount of leeway where we actually don't play around with the priorities that much, but we deal with a new quantity known as a system ceiling. So prior to that, I need to mention that the priority ceiling protocol runs on both uniprocessors as well as multiprocessors. But just to keep things simple in our analysis, we will focus on uniprocessors. But many of the results can be extended to multiple multi-core, multiprocessor scenarios as well, but that we will not do. So we define a system ceiling. So the definition of a ceiling remains the same. We define a system ceiling, which is the largest of the ceilings of all the resources that have been currently acquired at some time t. Let me just clear that and let me explain. So consider a number line, a timeline like this, and consider some time t here. So consider all the activity that was going on between t is equal to 0 and t. So a lot of resources were acquired. R1, R2, R3, and so on. Every resource has a ceiling. So we will have ceiling of R1, we'll have ceiling of R2, where ceiling retains its previous meaning. The maximum original priority of a task that may ever be interested in this now or in the future. So we find the maximum of all of these ceilings for all the resources that have been acquired by any task in the system. That is the CSC. So it's the max of the ceilings. This is the CSC. And clearly, if any resource is released, the CSC is recomputed. A resource can be granted or it can be given to a task if it tries to acquire it by the OS. The resource grant clause is like this. Any one of these conditions has to be true. The first is that the task holds a resource that has set the current system ceiling. Let us say the current system ceiling is 27. It means that a task acquired a resource. So the current system ceiling CSC was some other value. From that some other value, it became 27. So then this resource is called a critical resource. And after that, the task can continue acquiring resources. It does not need any permission, anything, because it holds the critical resource. Now assume that the task is just beginning when it hasn't acquired any resource. Then its priority, which is its original priority, needs to be higher than the CSC. Correct? So it basically means that if its priority is larger than the CSC, whatever is the current CSC at that point of time, let us say current CSC is 20, its priority is 25. If it is greater than it, then it can acquire the resource and also set the new CSC. If it will set the new CSC, it means that that resource has been acquired and that resource is critical. So what are the two things again? That the two resource grant clauses that we have. A resource grant clause is basically a condition that needs to hold. So what we have here is that I just continue and then let's say the current task T wishes to acquire resource R and the current CSC is let's say 20. If its priority is equal to 25, we are done. It acquires resource R becomes the resource for which the CSC is 25. Subsequently, it can acquire as many resources as it wants. That is because of clause 1, but when it's beginning, it has to acquire it because of clause 2, which means a high initial priority. So let's explain this in common terms, ordinary parlance. If the starting priority is high, greater than the CSC, which means the task is a high priority task, it can start acquiring resources. Once it has acquired one resource, our aim is to prevent second blocking. So it will continue to acquire resources, no issues, which is clause 1, subject to the fact that it started out with a high priority. So we will see that both of these are important clauses. And our main aim would be to prove that PCP does not have second blocking. in the sense that the first time a task tries to acquire a resource, it can get blocked, right? And that it can get blocked because either the resource has been taken by some other task or it is not satisfying these conditions, which means its priority is less than the CSC. So, but the second time it will not get blocked because there is no second blocking, which is something we will prove. The inheritance clause is exactly the same as the priority inheritance protocol, that if, let's say, one task is resource blocking on another task, then the lock holder gets the priority of the lock requester, assuming that the lock requester has a higher priority. And clearly, once resources are released, priorities are reverted back and the CSC is also changed. That is a is an implicit part of this definition. So let us prove a lemma first and then we'll prove the main theorem, which is that second blocking is not allowed. So assume a task T acquires a resource R at time small t. So this can be shown like this, that at time small t, task T acquires resource R. So clearly, let us assume that this is happening because its original priority is higher than the CSC at that point of time, hence it acquires the resource. So then let the set S at this point denote the set of all the tasks that have already acquired resources before T. So set S is a set of tasks that have acquired other resources R1, R2, R3 and so on before this time period. So let us assume that it is somehow guaranteed that task T is not going to block, right? So till some point in the future, task T will continue. It is not going to block on a resource. It can get preempted, but it will not block on a resource, right? So let me recap. At time small t, task capital T acquires resource R, and this was done because its original priority was higher than the CSC, right? So by clause number 2, it acquired a resource. Let us further assume at that point of time, a bunch of other resources were acquired by other tasks. Let the set of all of those other tasks be capital S. All right. Now, let's say somehow it is guaranteed that task T will continue without resource blocking. Then it is not possible for any future task which includes T as well as all of those tasks that are preempting T because of higher priorities to ever be interested in any resource that is acquired by a task in S. So let us say S has a bunch of tasks. So let them be, T1, T2, T3 and whatnot. Now all of them have acquired some resources. So basically task T as well as any other task that preempts it will never show any interest in acquiring any resource in this set. Any of these resources R1, R2, right, which were allocated before T, no task which is T and anything else that preempts it will ever show any interest in acquiring them. So basically, T is some sort of a separation point where anything that runs after it shows no interest in acquiring something that has been acquired before this point. So let's understand why. This is an important lemma which we'll use in the subsequent theorem. Let's see why. So after acquiring resource R, T will continue to execute. As per our assumption in the statement of the lemma, it will not block. It may, however, get preempted by a high priority task TH. Let us assume that TH is interested in some resource that has already been acquired. Or let's say T is interested in some resource at a later point in something which has already been acquired. But T will not be interested because it's going to block. And we are assuming that T will not block. So hence T cannot be interested, but TH can be. And TH is clearly preempting T. So one thing is clear, that given that at time T, TH was not running, otherwise T would have never run in the first place. At a later point of time, some high priority task th came, right? It could not have come at time t, because then task capital T would not be running in the first place. So the question is, can th be interested in any resource acquired by a task in S, which means all the resources acquired prior to time t. So the following relationships have to hold, right? The current priority of task T has to be the CSC at time T minus, which is basically epsilon before time T. That is how it got the resource in the first place, right? Which is as per our assumption that its priority was higher than the CSC. So it will be greater than CSC of T minus, which again has to be greater than equal to the original priority of TH. This is by definition because TH is interested in some resource, which means the ceiling of that resource, right, Rx, whatever that is, has to be greater than equal to TH's original priority, which is by the definition of a ceiling. Given that TH is starting afresh, TH's priority would be original priority of TH. So clearly, it is the case that ceiling of Rx is greater than equal to original priority of TH, and the CSC at T minus has to be greater than equal to all the ceilings. So this makes it amply clear that the current priority of task T will always be greater than equal to the priorities of any such task TH. And given that it is coming anew and afresh, TH will not be able to preempt T. Because it will not be able to preempt, it will not run in the first place. And if it will not run, then the question of it being interested, then it being interested and trying to acquire, that question also does not arise, mainly because it simply does not get a chance to run. So by definition, it does not become a future task because a future task has to be running. So of course, there are some other kind of corner cases we may want to consider where TH has acquired one resource, got second blocked while acquiring the second resource, and then task T released it. Such conditions are possible, but we are not considering this because we shall quickly see in the subsequent theorem that you are also assuming that there is no second blocking, and so this can be made a part of this that maybe we can add another rider to this, but I have not deliberately considered those corner cases because the context in which this lemma is called will make them clear. But for the sake of completeness, it should be added that I'm assuming there is no second blocking also. So if I make an assumption that there is no second blocking, then the chance of task T releasing something and then that task coming, that is also not there. And even if it is getting blocked for the first time also, then also, you will see there will not be an issue because all their priorities, including current priorities, will be less than the CSC. That is because the CSC is a maximum of everything that has been acquired up till now. So there is no way that any other task will come and show interest, because if it shows interest, then the current CSC at T minus would clearly be more than its greater than equal to its priority. And then task T would not have gotten the resource. So as I said, you can consider a few more cases, right, which deal with acquiring and releasing and so on. But this lemma is still going to hold that no subsequent task will show any interest in any task that has been acquired prior to T, primarily because of the definition of the CSC. If it shows interest, then clearly T cannot be greater than the CSC. So now we come at the main theorem, which is that PCP does not suffer from second blocking. So we will look at two specific instances. The first is assume that the first instance of second blocking in the system is a T block. Let us say task T1 acquired R1, which was its first resource at time T1. Subsequently, T1 gets blocked while it is trying to access resource R2, right? So which means that R2 has been acquired by task T2. And this can happen, let's say when. So let us consider the case when this acquisition happened prior to T1. So prior to small t1. So prior to small t1, the original priority of task t1 was also its current priority because it had not made any acquisition. This will be less than equal to the ceiling of R2, which follows from definition given the fact that T1 is interested in R2, which is going to be smaller than the CSC at T1, which again is from the definition. This is because by T1, T2 has already acquired R2. Hence, the CSC has to be greater than equal to the ceiling of R2. So this all of this follows from just from the definition of ceiling and CST. So what we see is that for T1 to be running at this point, the priority of T1 had to be actually greater than the CSC. There is no other way that it could have acquired because did not acquire a critical resource by then, which means that the only way that it can acquire is by clause number 2. So, but this is not the case. The priority of T1 is less than equal to the CSC, but we wanted it to be greater. It is not greater. Hence, it means that T1 could not have acquired resource R at T1. Hence, this particular condition that we are looking at is not possible, and we arrive at a contradiction. So, what is the sum total of what we are trying to say? What we are trying to say is that task T1 got blocked while it was trying to acquire R2. Why did it get blocked? Because this was the first such instance of second blocking. And T1 acquired its first resource R1 at time small t1. There are two choices. That T2 acquired R2 before this point or after this point. If it acquired before this point, then the CSC was set to a high value, which was clearly greater than equal to T1's original priority. And at T1, just before T1, the priority small t1, the priority of task t1 was less than equal to the CSC, which is follows by definition. So there is no way it could have been greater and it could have acquired the resource by clause 2 of the resource grant clause, right? Which says that the priority has to be greater than the CSC. That clearly did not hold. So this first condition will not happen. Consider the second condition, which is T2 acquired R2 after time small t1, which is basically this condition. Let me clear the ink. This means at this point T2 acquired R2. At this particular point, what could happen is that the reason it did so is because the original priority of T2 is greater than the CSC of T1. This has to be the case because, mind you, T1 had acquired R1 at this point of time. If T1 had acquired R1, then it clearly set the CSC. So the only option for T2 would have been that its original priority would have been greater than the CSC that was set at T1, right? That is how it would have gotten the resource because it did not have a critical resource at that point of time. T1 had it. Then what happens is CSC at time T1, small t1, is greater than equal to the ceiling of R1. This follows from the definition. The ceiling of R1 is greater than equal to the original priority of task T1, which means that if I consider task T2, its original priority was greater than, because note there is a greater here, than the original priority of task T1. Now we know that T2 cannot get blocked till T block. This means that T1 can only execute, right? So if some high priority task TH preempts T2. So let's look at the timeline once again. So the timeline that we are looking at is like this, that we have time small t1. At small t1, what happens is t1 acquires r1. Then at a subsequent time, t2 acquires r2. Then at time t block, t1 tries to acquire r2, but it fails in acquiring r2. And this is the first such instance of second block. So clearly at this point of time, T2 is executing and T2 is going to continue to execute. That is because it cannot get blocked, because it cannot get blocked before T block, because T block is the first instance of second blocking. So the only option for T1 to run is if T2 is preempted by some high priority task TH. And that high priority task TH somehow transfers its priority to task T1, right? Such that T1 can then run. One option is that TH blocks on some resource that T1 has acquired, like R1, and then its priority gets transferred to T1, and T1 then runs and ultimately blocks at T block. If that is the case, where TH would preempt T2 and transfer its priority to T1 via inheritance, let us see if this is possible or not. As per the lemma that we have proven, this is not possible because TH is showing interest in a resource that has previously been acquired. And clearly, this is an instance where we are not looking at second blocking. And furthermore, here, if you look at this lemma, let me just clear off the ink. So what are we seeing? We are seeing this task T, in this case, this is task T2, acquires, which resource would this be? This would be task T2 acquiring resource R2 at some time. Let's say this instance of time here is T2. And why is it happening? Because its original priority is greater than the CSC. That is exactly what is happening here. Because as you can see, given that T1 has acquired R1, T2 will not get a resource. But then its original priority is at the CSC at some point of time, maybe either for R2 or some other resource. And then it will continue to execute. So then at this point of time, S is the set of all the tasks that have acquired a resource before time T2. And let us see what is there in S. Clearly, all the time instance prior to time T2, task T1 is a part of S. So T1 is an element of S. And one of the resources that has been acquired in the past is actually resource R1. So resource R1 has been acquired in the past. Given that R1 has been acquired in the past by T1, the question is that can any future task, which in this case is TH, ever covet R1? Because only if it covets R1, then only it will block and transfer its priority to T1. But we have just proven that TH will never covet, which means will never try to acquire R1, right? And that is because of the logic in this lemma, which means that it will never be the case that any task TH will actually transfer its priority to T1 and boost it. That's not going to happen. right? Given the fact that the lemma says it will not happen, T1 will actually never get a chance to execute before T block. Hence, T1 executing, trying to acquire R2 and that not being successful, this is not possible. We have a contradiction. So, what do we see over here for the second case if I was to summarize at a high level? At the high level, the idea is T1 acquired R1 well and good, then T2 acquired R2 well and good. But once T2 has acquired R2, T1 will not get a chance to run until T2 has released R2 and pretty much finished. So the point is, how did T1 get to run? Because T1 got to run, hence its second block, but T1 will not get to run naturally because T2 is not blocking. T2 has acquired R2 and there is no second blocking till T block. It will run only if there is some case of a priority inheritance based priority transfer, which is something that we just stopped because of the lemma. And we just said that, look, that is not going to be possible at all. And given the fact that any future task will not covet resource R1, T1 is not going to get anything. So we can, of course, look at other corner cases of some other task getting released and then that transferring, but all of those things can be covered quite easily. And we thus have a proof that there is no second blocking in PCP. And then that means there is no chain blocking, which means that there are no deadlocks. That is the key idea of our long and somewhat complicated proof. So this is the bibliography for this chapter. So we looked at the gamut of scheduling, starting from conventional scheduling. We looked at conventional algorithms, FIFO, and so on, random. And then we looked at other algorithms that have some guarantees like shortest job first, SRTF, and so on. We looked a lot at synchronization. So we have in fact actually covered a lot of distance. And after synchronization, we looked at Linux's CFS scheduler. And then we looked at real time. So we have done a lot in this chapter. So what we'll do in the next chapter is we will focus on memory systems.